So this is our last section of week 6, which means that we are finally at Stokes' theorem, which is the most important of the results that you'll study in multivariable calculus. So Green's theorem gives you a way to convert a line integral around a flat curve in a plane to a double integral over the region that it encloses. And Stokes' theorem sort of does the same thing, except everything is now in 3 dimensions. So you still have this curve, which is still oriented sort of counterclockwise. Like if you're looking down on this, it's oriented counterclockwise. And the only difference is the surface that it encloses is not limited to a plane surface. Now we have this curvy surface. Basically, Stokes' theorem gives you a way to convert this single integral into this double integral. And we're going to sort of just do 2 basic examples of this. So we're not going to go into all the details because Stokes' theorem gets real complicated real fast. So a lot of the information in this section I'm going to give you. For example, I'm going to give you the normal vectors here instead of us computing them. We will compute the curl. So I'll give you like a little refresher on how to do that. But one thing that's sort of important to note here, even though we're just explaining this sort of on the surface, is a lot of times in the examples, will write the left expression here as f dot dr around a closed curve. That's one of the ways that we'll express the left side of this. And the problems, a lot of times, are going to use this phrase, the work performed by the vector field on a particle that traverses the curve. And that's because this expression, this single integral around this curve of f dotted with dr around the curve, or f dotted with the unit tangent vector, gives you the work performed by this vector field f on a particle that traverses around the curve. So like you have this vector field pulling the particle this way or another way, depending on what the vector field does. It's performing work on the particle. And if you want to find the amount of work, if you want to add up the work on all of these sort of like infinitesimally small quantities of work all the way around the curve, that's given by this integral. And an easier way to compute it is to dot the curl with the normal vector and compute a double integral instead, and this is what Stokes' theorem gives us. So in case you don't remember how to compute the curl of a vector field, curl was in the same section where we learned the divergence. So we learned the divergence of f, and we learned to find the curl of f. And divergence was a dot product, and curl was a cross product. And when we're computing a cross product, it's the determinant of this 3 by 3 matrix. So remember, when you're computing the determinant of a 3 by 3, you write the first column again and the second column again, and then you do the little, let's see, it's like cross, 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 minus, cross, 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 like that. So let's just start with an example of just the curl. So if you want to find the curl of this vector field, we're going to start with this 3 by 3 matrix. So I, J, K at the top, and then the partial with respect to x, the partial with respect to y, and the partial with respect to z. And then I just list my components across the bottom. So x squared, and then 4xy cubed, and y squared x. And then since I'm going to do a determinant here, I'm going to write the first 2 columns off to the side. So now, to compute the curl, I'm going to do cross this way, plus, cross, plus, cross, like that. So I'll start there, and this is going to give me some vector. So I just means the first component of the vector, and then partial with respect to y of that first component. Partial with respect to y of y squared x is my first component. I know it's the first component because it goes with the I. And then j, my second component, is the partial, oops, with respect to z of x squared. And my third component, k, is the partial with respect to x of 4xy cubed. Now I'm going to do the same thing again, except the negative crosses. So I'm just going to write underneath this minus and then make another vector with 3 components. So this first cross is the k component, which means I'm going to put it right over here in the third component place of my second vector. And this k component is going to be partial with respect to y of x squared. And then minus, now here's the I component, so here, partial with respect to z of 4xy cubed. And then the j component, so second component, which is going to be partial with respect to x of y squared x. And then I just need to figure out what these things are and actually subtract them. So this first vector, partial with respect to y of y squared x, is 2xy. And then I'm going to do partial with respect to z. I'm going to do this component by component. So first component minus first component. Partial with respect to z of this 4xy cubed is just minus 0 because there's no z component there. Now partial with respect to z of x squared is 0 minus. Partial with respect to x of y squared x is just y squared. And then partial with respect to x here is 4y cubed minus, and partial with respect to y of x squared is 0, which gives me a final answer. The curl of f for this example is 2xy, negative y squared, and then 4y cubed. So there's the curl. And the reason that I wrote this example first is because in the second example here, we're actually going to use Stokes' theorem to compute this. So I'm trying to use the same phrasing that you'll see in a problem. So find the work performed by the vector field, right? So that's asking you to do an integral of f dot and then this little distance component around a path. And then let's see, the path says it traverses the rectangle C in the plane z equals y. So the zy plane, so we're going to see some sort of diagonal zy plane going on here. From 0, 0, 0 to 0, 3, 3, so nothing in the x direction, 3 in the y direction, 3 in the z direction, to 0, 3, 3, to 1, 3, 3, so here, so I went over 1, over 3, up 3, here, and then to 1, 0, 0 here. So it's like this path. So here to here to here to here. So there is our picture, and one thing you'll notice, if I trace out the direction that I just wrote those in and that they read, this path as it is now is not counterclockwise. This path, like if we were looking down this way, this path is going clockwise. Which is important because Stokes' theorem says don't compute this single integral. Instead, compute the double integral of the curl of f, which we just found. This is the same vector field that we started with, so we just found this curl. We can use it from the first example, dotted with a normal vector. And the normal vector really helps us to determine the orientation. If I chose the normal vector, you don't have to write this on your paper because it's wrong. If I chose this normal vector, like if you're standing on this normal vector, the particle is traveling around you in the clockwise direction. Like if you're standing at the tip of this and watching this particle traveling around this path, this rectangular path, it's traveling in the clockwise direction, which means it's not going to work for us. It kind of tells us that our normal vector has to be going down this way, and now if you're standing at the end of this normal vector, now you're watching this particle travel in the counterclockwise direction. So that's really important, and we found the normal vector, we found the curl just now in our previous example. We found that the curl is 2xy negative y squared and 4y cubed. And I will give you the curl, the normal vector, the normal vector in this case is going to be 0, 1, negative 1. There's our normal that's pointing in the correct direction. You can see it goes over in the y direction and then down in the z direction. That's going to be the correct normal for us. So I just need to dot those together and then think about my limits. And the thing that's going to help me with these limits is projecting this surface, this rectangular surface, onto the xy plane, because all of this is going to be converted into xy. So when I convert this down, when I project this down onto the xy plane, I can see that x goes from 0 to 1, x goes from 0 to 1, and y goes from 0 to 3. So here's going to be a square flat region. I'm going to convert my integral using those. So let's dot these together, and then I'll actually take this integral with limits. So when I dot two vectors together, remember that just is like first component times first component plus second times second plus third times third. So first component times first component gives us 0. Second component times second component just gives us negative y squared. And third component times third component gives us minus 4y cubed. And actually, I don't need to do that. Let's actually put in limits. So when I'm integrating this, as I said, I can see that y goes from 0 to 3, and since this integrand only has y's, I'm going to deal with that first. Y goes from 0 to 3, and my first integration is going to be with respect to y. And when I'm done with that, x goes from 0 to 1, so my second integration is going to be with respect to x. So let's start with just the y integration here. This becomes negative y cubed over 3 minus so it's going to be negative 4y to the 4th over 4. In other words, just y to the 4th. So let's plug in limits here. This is going to go from 0 to 3. And when I plug in those limits, I'm going to get y to the third, so negative 3 to the third is 27. But over 3, I'll simplify that, and then minus 81. When I plug in 0, the whole thing goes away, so this becomes negative 9 minus 81, or in other words, negative 90. And then I need to integrate that with respect to x. So just from 0 to 1, negative 90 with respect to x. That's my last integral. And that's a pretty friendly one, because that just becomes negative 90x evaluated from 0 to 1, which is just negative 90. And that is going to represent the work done by this vector field on a particle that travels around that weird rectangular path in 3 space, except we know that we don't have to really worry about like a work computation, because we'll just convert it to a double integral using Stokes' theorem and compute the double integral of the dot product of the curl with the normal vector. Normal vector being chosen so that when we look down from it, the particle is traveling in a counterclockwise direction. So let's do one more example of Stokes' theorem. This one's kind of interesting because it says verify Stokes' theorem. So what that means is I'm going to do my computations in 2 different ways and verify that they're actually equal. So my first integral is going to be taking a single integral around a curve of the vector field dotted with sort of my little differential vector. So dx, dy, dz. And then my second integral is going to be the integral of the dot product of the curl. So I'll get to that in a second. My first integral, let's actually write out the path. So C is the positively oriented circle, x squared plus y squared equals 4, which is this circle of radius 2 in the xy plane. And Z, the surface that it's enclosing, is the portion of the paraboloid. So it's like a parabola kind of, but it's like three-dimensional. Like it comes down this way and this way as well. And the height of this paraboloid is 4. So here's our surface. The particle is traveling this way. It says it's positively oriented, which means when we're looking down at it, the particle is traveling in the counterclockwise direction. So that's important because it tells us that our outward normal is just sort of the regular outward normal this way. Everything makes our particle where it's supposed to be. So let's do the first integral. So I'm taking my dot product of 2z, 3x, my vector field here, and 5y. My dot product was sort of my normal differential vector, so dx, dy, dz. And then I'm going to integrate that around this path, this circular path right here. So this is going to give me an integral of 2z dx plus 3x dy plus 5y dz around a circle. Now since this is a circular path, I'm going to convert this not exactly to polar coordinates because there's a z component, almost like to cylindrical coordinates. So I'm going to use the conversion. X is going to be equivalent to 2 cosine of t. I'm putting the 2 in the front because it's a radius 2 circle. Y is going to convert to 2 sine of t. And then this is actually going to be pretty easy for us. Z doesn't change at all. So z is just constantly 0 everywhere around this circular path because it's in the xy plane. So when I do that, dx converts to 2 sine of t dt. dy converts to, negative. dy converts to 2 cosine of t dt, and then dz, of course, is 0 because there's no z component. So this circular path is going to end up all being in terms of t. T is going to go from 0 to 2 pi because it's giving us all the way around the circle. And now I just need to sort of plug in this conversion. Now 2z is just 0, so I don't even need this first expression at all. 3x is going to turn into 6 cosine of t, because 3 times 2 cosine of t, times dy. So times 2 cosine of t dt. And then 5y is actually important, but dz is 0, so I'm not going to put that in there at all. So it's like plus another 0. So this integral becomes the integral from 0 to 2 pi of 12 cosine squared of t dt. Now, you can evaluate this using integration by parts because it's cosine squared. There isn't really like a good u substitution to do, but integration by parts works for this, or you can plug it into your calculator. If you want to pause the video now and integrate by parts by hand, you can do that. But the answer to this entire thing is 12 pi when we're done. So if we were to evaluate this, which you might notice, I mean, this gets us to kind of like not a terribly friendly integral, something we have to integrate by parts, but still a simple single integral, although we had to do a bunch of conversions to do that. So now let's go back and do the exact same computation, but this time over this paraboloid surface. Because Stokes' theorem says let's do a double integral over the surface instead, and we should get the same answer. So again, I'm going to give you a lot of this, but let's do this the second way. So Stokes' theorem says we need to first find the curl. Now the curl, in this case, is going to be the determinant of this 3 by 3 matrix. So partial with respect to x, partial with respect to y, partial with respect to z, and then our vector field for this example is 2z, 3x, 5y. I'm going to write the first and second column again, just because I know I'm doing a determinant. Partial with respect to y, and then 3x, and then I'm going to go cross this way, cross this way, cross this way, and those are positive. So first component is partial with respect to y of 5y, which is just 5. Second component is partial with respect to z of 2z, which is just 2. And third component is partial with respect to x of 3x, which is just 3. And then I'm going to do minus the other 3 crosses. So cross this way, cross this way, cross this way. Although this is really convenient because you'll notice partial with respect to y of something that doesn't have a y, partial with respect to z, no z here, and partial with respect to x of something that doesn't have an x. All of these are 0. So we found the curl really easily. It really is just the vector 5, 2, 3. And that's the first part of our Stokes' theorem double integral computation. The second part is the normal vector. And again, I'm going to give you the normal vector. There's kind of a section that we didn't totally cover on some easy ways to find normal vectors of specific surfaces that are written in specific forms. So I'm just going to give you the normal vector in this case that we're going to use is the vector 2x, 2y, 1. So there's our normal vector, and Stokes' theorem says integrate over this two-dimensional surface, and actually we're going to project it down and integrate just over a flat plane region of the dot product of the curl dotted with the normal vector. So actually that should be an A, because we're going to use an area element here. So I'm going to dot those together, but let's look at our region first. When I project this surface down, it projects onto a flat circle, and that's the region that we're going to integrate over here with Stokes' theorem. So that's going to make our limits kind of easy in just a second, but we are going to have to convert to polar coordinates before we integrate. So integrating this dot product, it's going to go first times first, which is 10x, second times second, so 4y, and third times third, so plus 3. Now I just need to figure out my limits. And again, if you remember how to convert to polar coordinates, x converts to r cosine theta, y converts to r sine theta, sine theta, and we're in a plane, so there's really no z component. And also dA converts to r dr d theta, which we talked a little bit about in the Green's theorem section. So now I'm just going to make my conversion and put in some limits. Now this is a circle of radius 2, so when I'm converting to polar coordinates and I'm starting to think about my limits, r is going to go from 0 to 2 and theta is going to go from 0 to 2 pi, because we're going all the way around the circle and the circle is radius 2. Now, everywhere I see an x, I'm going to put r cosine theta. And everywhere I see a y, I'm going to put r sine theta. Then I have plus 3 with nothing attached to it. And then dA becomes r dr d theta. So I'm just going to distribute this r before I actually integrate. We'll go from 0 to 2 pi, 0 to 2, and this is going to become 10r squared cosine theta plus 4r squared sine theta plus 3r. And then we'll integrate first with respect to r and second with respect to theta. So my first integral is with respect to r. So everything with a theta is held constant, and this becomes 10r cubed over 3 cosine of theta plus 4r cubed over 3 sine theta plus 3r squared over 2, and I just need to evaluate from 0 to 2. Now when I plug in 0, this entire expression dies, so really this is just coming down to plugging in 2. And when I do that, I plug in 2 everywhere here for r, r cubed becomes 8. This is 80 over 3 cosine of theta plus, and when I plug in r, or 2 for r here, it also becomes 8, so 4 times 8 is 32. 32 over 3 sine theta. And then r squared is 4. 4 times 3 is 12. And 12 over 2 is 6. So there's my new integrand. And since I made so many computational errors on the last video, I'm just going to check real quick, but that's right. So then I'm going to go back and do my second integral, so 0 to 2 pi, of this new integrand. But now this second integral is with respect to theta. Not too many difficult computations. It's a little bit tedious so far, but nothing crazy in this double integral the way that we have it. It's nice because we were able to convert to polar coordinates. That makes this a lot easier. So 80 over 3 is just a constant that stays. Cosine integrates to positive sine. Sine integrates to negative cosine. And 6 integrates to 6 theta, and then we will evaluate from 0 to 2 pi. 0 kills off the whole thing, so really all of this just comes down to plugging in 2 pi. No, that's not true. 0 doesn't kill off the whole thing. 0 doesn't kill off this part. Okay, so we really do have to plug in both. 2 pi, sine of 2 pi is 0, so that kills off the first one. So this would become negative 32 over 3. Cosine of 2 pi is 1. And then 6 times 2 pi is 12 pi. So there's our first portion of this. And then I'm going to have minus, well, sine of 0 is 0, so this first component dies off. Minus, and then cosine of 0 is 1. So this would become plus 32 over 3. And 6 times 0 would be 0, which shows us that now we have negative 32 over 3 and then positive 32 over 3, so those two cancel. And this entire thing turns out to be 12 pi, which of course we knew that it would because we were verifying that Stokes' theorem was true, and in our first computation we got 12 pi. So that just shows you that we were able to do the computation in 2 different ways and get the same answer, and that's what Stokes' theorem shows you that you can do. So again, Stokes' theorem gives you a way to take a sort of curvy surface enclosed by a curve, and instead of finding an integral around the path, to actually do a double integral around the surface. So project the surface onto a plane and compute a double integral that way. And at this point, I think that you can do all the rest of the exercises. So again, number 8 is kind of like what we just did. So you're verifying Stokes' theorem. So you'll do 2 different integrals. One of f dot dr and then you'll show that that's equal to the double integral of, whoops, the curl of f dotted with the normal vector. Nope, dA. Number 9, I think, is the same thing. So yeah, verifying again Stokes' theorem, so 2 different computations. And I'm not sure if there's a number 10. Oh, there is. And then number 10, you can decide whichever computation you would like to do. I would recommend on this one that you find the integral of the curl, the double integral of the curl, dotted with the normal vector. I think that's going to be the easiest way to do this one. If you have questions about Stokes' theorem, which I'm sure that you do, you should either email me or come to our office hours this week, and we will have an extra office hour, I think, just because I'm getting this video out to you so late.